In this video, we're going to have a brief introduction to trees. In particular, we're going to take a look at mechanisms for searching through trees, including depth-first search and breadth-first search. So let's talk about how trees come up in computer science at all. And the gist of it is, as I'm sure you are unaware, computers are really fast. And for a long time, the process of programming was that computers don't need to be smart because they are just so fast. And so many algorithms begin by just listing all possible cases, which would be a ridiculous workload for a person to do by hand, but is nothing for the computer since it's so fast. And so we just have all possible cases organized in some manner, and we have the computer walk through them one by one. And of course, one of the greatest benefits of this is that if you've checked all cases, when you're finished running your program, you can feel reasonably confident that you have all solutions because you've been through everything. If the computer does not find it, it isn't there, barring that there's an error in your code. So that's one of the key things of algorithms is we need to be guaranteed that we will find the right answer always, and checking everything is one really good way to guarantee that that occurs. Because we could never really go through all cases by hand, and that's the reason we're having a computer do it, we tend to take a step back from the program and try to visualize exactly what the computer is doing without having to do it ourselves. And so we as people like to draw visual diagrams of all possible cases as a tree, because most often we're building these collection of all possible cases by doing some sort of recursion and having sort of steps of the process, and the steps tend to be the various levels of the tree, and then what is being done and how many options are being created is something that's done by a recursive function. So we tend to organize the levels of the function call in this horizontal manner and visualize all possible cases as paths in these trees. So if this is the root of the tree, and then we get all the way down to these things that are called the leaves of the trees. These are sort of the final destinations, the very last things you could be, and generally your cases are sitting here amongst the leaves. When we talk about doing what's called a depth-first search, we're going all the way to the depth of the tree, from the root to the leaf. And because our computer needs to be organized in the way that it's handling all possible cases, we tend to walk through the tree something like I've envisioned here. Here's the first case that we reach in the leaves, and then this case. And then once we reach end of one branch, we go back a level and we hop over and we move to the next branch, and so on and so forth in this particular manner. So a depth-first search is going to start at the root, it's going to make its way all the way to the leaves, and it's going to do that in a sort of left to right manner, the way that I have it drawn, in a very methodical way. A breadth-first search is going to be walking the tree in a different way. Instead of walking top to bottom and doing a whole bunch of vertical cuts of the tree, the way that I have it drawn, a breadth-first search is going to be making these horizontal passes through the tree, and instead of going all the way down to the leaves on a very first attempt, it's instead going to go through the levels completely one by one. So I've sort of drawn an animation of that here. So it starts out with those and it goes all the way across the first level, and then once we're all the way across that first level, we're going to jump down to level 2 and start going across left to right. Now, with both types of algorithms, we can often do what's called pruning the tree, which is something we've done before. So depending on the context of your problem, it may be the case that you identify at some level, and I've identified it with a red marker here, that something's gone wrong or something is going to make everything from here on out impossible. And so if I were in a depth-first search and I had identified at this node that something was going to be impossible, what that would do for me is say, I don't really even need to check any of those branches of the tree. None of them is going to lead to an outcome I desire, and I could short circuit and head back to this branch. And it may be the case I've drawn it relatively low down in the tree, but it could be up higher and give you lots of savings. If I were envisioning that same difficulty point in a breadth-first search, because of the fact that I'm checking layers at a time horizontally, if that same point were a problem point in a breadth-first search, it would eliminate for me everything, not only from here on down, but everything in this direction as well. So I'd say, okay, I've already reached a problem here, or I've already found, and in the example we'll see for breadth-first search, we're not necessarily finding a problem, but we'll say if I find a solution here, then I can cut off the whole top, I guess, of this tree, and I don't need to search any further because I've found what I'm looking for right here. So just to give a few very specific to our class examples of depth-first search and breadth-first search, we've done a lot of puzzles like skyscraper puzzles, or finding Latin squares. And we have done that from a depth-first search perspective, where we thought of all possible Latin squares as the leaves on the tree, and we were going down and filling everything in and then just getting to that leaf and saying, are you a Latin square, are you a Latin square, are you a Latin square? So we needed a depth-first search for puzzle solutions because something that was not an entirely filled in puzzle, which would be something at a higher up level, would not be a solution. It's incomplete, and so there's no real way generically to assess its accuracy until we're all the way down at one of those leaves. But the example we'll be looking at this week is going to be something that is a good fit for doing a breadth-first search. And what we're going to be talking about are currency exchange scams. We put a little Office Space reference in here because there's something of that nature in that movie, and it's worth checking out in your free time right now. So let me show you what we're going to be doing with currency exchange scams. In a very simple way, I've put a picture up here. I'm imagining that A, B, and C are different currencies. Dollars, euros, Canadian dollars, whatever you want. They're just currencies. And what I've put inside this table, if I have one of currency A, let's imagine that that would yield 1.2 units of currency B and 2 units of currency C. So I put those values in here. Now, most often is the case, if 1 unit of currency A is worth 1.2 units of currency B, we would expect 1 unit of currency B to be equal to 1 over the value that's right here. However, if you actually do the computation 1 divided by 1.2, that turns out to be 0.83 with the 3 repeating. What you will find most often with currency exchange is that when you actually multiply these two values together, you get something that's a little bit less than 1, and that's considered the cost of doing that transaction. So it's normally a really terrible decision to take 1 unit, exchange it for something else, and then trade it right back. However, as these values are changing constantly, if somebody were to change and update this value before they got around to updating this value, and this increased a little bit, it could bump this number over 1, and if you did your currency transaction in that very instant, you'd gain a whole lot of money. And the story doesn't just stop there. So for example, if you take a look at currency B to currency C, so let's take a look at 1.603 times 0.62. Same issue there because of rounding error, we're a little bit less than 1. However, what happens if I take currency B, exchange it for currency A, then take currency A and exchange it for currency C? So I take B and I exchange it for C. I then take currency C and exchange it for currency A. And then I take currency A and exchange it for currency B. And I get a little bit more than 1 there. And so I didn't get this through a 2 currency swap transaction, but I was able to get a number a little bit bigger than 1 via a 3 currency transaction. And so really what we need to do is think about all possible ways to exchange money in cycles of 2s or 3s or however long makes sense, and take a look for these anomalies where when we perform these roundabout multiplications, we get values more than 1. If we were to trade currencies in at that exact moment, we would make money just by changing out money and then converting it back. So that's a very simple introduction to depth-first search and breadth-first search and trees and how and why they come up in computers. There are way better resources out there than this, but hopefully this gets you started.